First, let's pause and think. What comes to your mind? We are given a quantity of air that changes temperature, and the question is, what is the enthalpy change of this air? Let's pause here and think what we already know about this. Well, I hope you were able to recall that enthalpy change is equal to the heat exchanged under constant pressure. Here, with a human breathing, we can assume that it's on Earth and we are under constant pressure of 1 atm. So then our job of calculating the enthalpy boils down to calculating heat when air was going from 5 degrees to 27 degrees Celsius. In equation, we can write like this. Delta H is equal to QP, and also we can recall QP can be calculated by multiplying the constant heat capacity, quantity of the substance, many times we note it with an M, and then the temperature change. The temperature change being the final temperature minus the initial temperature, like that. Here, you have to also note that this quantity called M has to match the unit that is used for the heat capacity. Here, we are given heat capacity of 20 joule per K per mole. Therefore, the unit of the quantity is mole. So you have to use the quantity in moles in our calculation if you want to directly plug in and multiply with the CP that's given. So then the question now is, how do we do that? How do you get the mole of the air in this problem? Let's pause again and think. Yes, I hope you noticed that we can get this from the molar volume condition given. What do I mean by molar volume? Here, the volume of 1.00 mole of air molecules at 1 atm and 5 degrees Celsius is 23 decimeter cube. That is basically telling you for each mole, this is the volume, and that's called molar volume. And under constant pressure that we are talking about, PV, as you know, PV equals nRT all the time for air and ideal gas. And so when pressure is constant and let's say temperature is 5 degrees Celsius constant temperature, then the volume is going to be proportional to N. So we can say V1 to N1 in one condition should be equal to V2, N2 for a different N. In other words, we can write this ratio equation with the given condition. So we are basically given the fact that for 23 decimeter cube is equal to 1 mole under 5 degrees Celsius. Therefore, we can Therefore, if we got 0.51 decimeter cube, we can calculate how many mole that is. And you know how to deal with it. The product of these two numbers and these two numbers should be equal. And with a little arrangement, we can say X should be equal to 0.51 decimeter cube times 1 mole divided by 23 decimeter cube. Okay, don't plug in these numbers into calculators yet. Now let's actually go back and put these together in this equation for the delta H. So delta H is equal to QP, and QP is equal to Cp times the quantity times delta T. So we write that, and then we write the corresponding numbers we got. So 20 joule per mole per Kelvin. The mole, M quantity as a mole, is going to be 0.51 divided by 23. And that is actually indeed in the unit of mole, because this decimeter cube in this X cancel out. So again, this is in the unit of mole. And then for delta T, we have a final temperature of 27 and initial temperature of 5. Now you may ask, oh, Professor, you said we should use Kelvin in the calculation. Well, in here, it's okay to use temperature simply in the Celsius and just say you are subtracting 5 from 27, because for the differences between the two temperatures, the Celsius and Kelvin are the same. You can easily see that, right? In the Kelvin, 27 is 27 plus 273, and then 5 degrees Celsius is 5 plus 273. So if you take the difference between the two, this and this cancel out. So from the beginning, you don't have to write that down. So yeah, so now obviously 27 minus 5 is 22. Now you plug in, this is a good time to plug in the numbers into calculator. 20 times 0.51 divided by 23 times 22 Kelvin, you would get basically 9.7565 joule, and you can confirm that final unit here. Mole cancel out, Kelvin cancel out. The only unit that remains is the joule here. And if you are to punch this in Canvas, you also need to make sure that you have the correct significant figure. And since the significant figure of this calculation, the limiting factor is 0.51, so we would write it in 2 sig fig from the 0.51, so it's gonna be 2.8 joule, and that is it. That's our answer. You basically calculated the enthalpy change of the air that is breathed in and out during that process. Okay, good work today. I hope it helped. See you next time.